welcome back to another Friday seminar series. It's my pleasure to introduce Professor Hokeun Kim from Arizona State University. And just to do a little bit of an introduction for him, he's had an interesting, very dynamic career. He received his PhD degrees in ECS from UC Berkeley in 2017 with a focus on distributed cyber-physical systems and IoT security, which we'll be talking about, hearing about today. Since then, he was at Google for a few years, up until 2021. After that, he went back to his home country of Korea. He was a professor at Hanyang University for a few years. After that, he has recently moved to ASU a few years ago, and he's been there since then. He's had a very dynamic career, and he's had also a very fruitful career. He has received the ACM IEEE Best Paper Award and IEEE Micro Top Picks honorable mention for his research contributions to cyber-physical systems and computer architecture research. So I'm very excited to hear about what he's going to tell us today. So thank you.
Thank you very much, Sang. Actually, Sang and I have known each other for 20 years. Like we went to the same university for our undergrads. Anyway, thank you everyone for having me here and also joining seminar. And actually, I was here 2 weeks ago for a conference, CPS IoT Week, and it's good to be back in 2 years at UCI campus. They're very beautiful campus. So today, as Professor John introduced, I'll be talking about my research around the security and safety of internet-connected critical infrastructure. So, as Professor John just introduced, I studied at UC Berkeley, and my dissertation topic was safety and security of Internet of Important Things. I'll talk more about what this means. This is related to critical infrastructure. And right now, I'm at Arizona State University. I still work on security, cyber-physical systems, and also real-time and distributed systems. When I was in industry, I worked on Google's Safe Browse team, where we did research on detection and enforcement mechanisms for phishing and malware attacks to protect internet users. And these work are actually all related to the topic that I'll be discussing today. So I brought up the term critical infrastructure. So what is critical infrastructure, and why is this so important to us, to computer scientists and engineers? And this is the National Security Memorandum, NSM, from April 2024. And so you can see here, the government, the American government really cares about critical infrastructure's security and resilience. And more recently, there was an executive order with referencing this NSM 22, the National Security Memorandum. And here it mentions American infrastructure needs to be enhanced for national security and more resilient nation. And this includes strategic investment to enable risk-informed decisions against global and dynamic threats and hazards. So I'll be touching these topics more later. And going back to the memorandum, you'll see that the stakeholders of the critical infrastructure or examples of the critical infrastructure are very diverse. It includes manufacturing systems, defense, emergency services, energy, infrastructure, food and agriculture, healthcare, even IT information technology itself, or nuclear facilities, transportation systems, and water and wastewater management systems. So if you look at these stakeholders and examples of critical infrastructure, you will see some common characteristics that includes that they are related to physical infrastructure, not just the virtual infrastructure. And they are very closely related to our daily life and our society. And it's not something that came out recently. The critical infrastructure has been there for decades, And now they are equipped with computation, intelligence, and communication. They are getting smarter and more intelligent. And as you can imagine, failures in this, excuse me, sorry. Yeah, failures in this critical infrastructure can lead to devastating consequences. It won't be just financial losses. It can lead to losses of human lives or our society systems. So that makes these critical infrastructure systems juicy targets for bad actors. So yeah, so I just introduced what critical infrastructure is and why is it so important to us. So let me relate that to our major computer science. So there have been lots of computer science buzzwords around the critical infrastructure, including embedded systems, real-time systems, cyber physical systems, or Internet of Things, and also distributed systems or edge or full computing. I'm pretty sure that most of you have heard about at least a few of these buzzwords, right? They sound familiar. And there were even more buzzwords used in different contexts, including safety critical or mission critical systems, such as the Mars rover, Perseverance rover, and its Ingenuity helicopter, and industrial IoT, used for manufacturing systems or industrial control systems, and something called operational technology. This is a term more widely used in industry rather than academia. That includes industrial control systems like SCADA, supervisory control and data acquisition, or programmable logic controllers, or even more buzzword industry 4.0, just convergence of this operational technology and the information technology. But since we are academics, I'll focus more on these CS buzzwords more widely used in academia, including the term cyber physical systems. So yeah, let me just briefly go over these buzzwords. So let me start with the embedded systems. This term has been there for a very long time, and it refers to computing systems with a special purpose. For example, mobile phones, control systems, home appliances like washing machines, refrigerators, and a subset of embedded systems called cyber physical systems refer to the computing systems that have interaction with the physical world or the humans. So by nature, they are special purpose mostly, although not all embedded systems are cyber physical systems, and these systems include manufacturing systems, healthcare, biomedical systems, avionics, airplanes, or cars. And there's a term called real-time systems. So this is not only related to embedded systems and cyber physical systems, but this is also related to general purpose computing systems. For example, Zoom is one of the real-time systems because you want to have the response of the other end in real time. And these systems are characterized by time sensitiveness, and sometimes they are safety critical or mission critical, meaning that these failures can lead to more devastating consequences. And timeliness, the timely response is part of the correctness requirements of these systems rather than just performance metrics. So I talked about embedded systems, cyber physical systems, and real-time systems. Moving on to networked or distributed systems. And these systems are connected to each other over the computer networks. And nowadays, many of these cyber physical systems, real-time systems are connected to each other. And these special purpose computing systems are also connected to general purpose computing systems. And often people, these are the other buzzwords I briefly mentioned earlier. I think they are often called Internet of Things, right? These are connected to the internet, and the things can mean a variety of things. But however, because if you think about the term IoT or things, people tend to think about small stuff like sensor nodes or less critical computing system. So there's another term coined earlier. I think it was coined 2010s called Internet of Important Things to emphasize that some of these things are critical and very important to our society and our daily lives. So I'll be using this term a lot, but it is basically another term of internet connected critical product. So let me talk a little more about cyber physical systems. This is one of my major research areas. So cyber physical systems, as I briefly talked about, they have interaction with the physical world, okay? Not just the computation, using sensors and actuators. So sensors are tools to read the environments of the computing system, and actuators are the mechanisms to have an impact on the physical world. And many of them are safety or mission critical, and the examples include cars, planes, warships, or manufacturing systems. And they became networked because of many needs, but primarily to cover a wider physical region. So for example, if you want to install a system, cyber physical system for a building, you don't want to have lengthy wires all over the building, right? It's easier to use the wireless communication or even wired communication between these systems. So they became networked. And nowadays, they are even connected to the internet and the cloud. And this is also where the term Internet of Important Things, or IoT, was brought up. So it includes transportation system, so much larger scale, and we can also leverage the data or the intelligence from the internet or the cloud, power grids, environmental monitoring, or remote healthcare. So from now on, I'll be using the term internet connected critical infrastructure and IoT interchangeably. Oh, by the way, if you have any questions, please feel free to interrupt me anytime. So yeah, let's focus on internet connectivity. So what does that mean, and why do we want to have internet connectivity for our critical infrastructure? So there are lots of benefits from internet connectivity, and one of them is that this critical infrastructure can leverage the intelligence and data coming from the internet. Right? And we can even leverage the computation power of the cloud. Right? And it allows collaboration between these critical infrastructure systems, or even with the general purpose computing systems over the computer networks. And it allows the critical infrastructure to cover much wider physical region using the single system. And it also allows remote control and operation. And this is especially useful for when the physical operation is not safe for humans. You can think about what happened during the COVID-19 era, and also in case of nuclear incidents, when the human operator is not safe for human operators, we can let them control and operate this critical infrastructure over them. So it sounds very useful. However, I really like this figure and the term of the phrase that internet is a wilderness, right? Internet has lots of useful information, but internet also has lots of false information or even hostile information. And there are lots of not just the information, there are actually executables like malware that can damage your computer. So there are lots of full of bad actors, and there is a restless attempts to break in. So we need to be careful when we try to connect any system to the internet. So yeah, just briefly mentioning that this internet connected critical infrastructure by nature has lots of rich computer science research agendas, including cyber physical systems, my home research community, and distributed systems, and real-time systems, and even cybersecurity. So yeah, that was the introduction to the research landscape of the internet connected critical infrastructure, or IoT. let me move on to the first main topic, risk threats, and how these attacks work in reality. I mean, these attacks on the internet connected critical infrastructure. So this is a report from the Office of Director of the National Intelligence last year, and it visualizes the attacks, recent cyber attacks on American infrastructure, including agriculture, education, energy, healthcare, manufacturing, government facilities, telecommunication, and water management systems. And as you can see, California was one of the victim states of these cyber attacks on our critical infrastructure. And let me go over. Oh, actually, let me share the even more recent version of report from Department of Homeland Security, where they pointed out that we expect this kind of adversarial attacks will increase, and they can potentially disrupt the critical functions of the government and our critical infrastructure. And they also saw the number of attacks or attack attempts have been increasing on this U.S. critical infrastructure. So yeah, let me go over some example attacks that happened recently. So first one is the attack by activist group called Cyber Avengers. This is not a typo. They have 3 in Avengers, and they targeted certain programmable logic controllers made by a company called Unitronics, and they hacked into the water system of a city of Aliquippa, Pennsylvania, in November 2023. And they targeted this remote water station, and instead of having this control system, touch screen based control system, they showed this scary visualization. So yeah, the attack worked, and it certainly disrupted the water management systems of the city in Pennsylvania. Yeah. So, and there was a more recent attack on a water system of 3 towns in Texas, and one of them is Muleshoe. So sometimes we call it Muleshoe water system hack, and it happened in April 2024. Although the previous attack did not really cause the physical harm, right? It made the water system unavailable. But this one was even more nasty because it actually caused the water to overflow in the water management. So it caused the physical harm. And there have been attacks on Texas Power Grid and Hawaii water utilities recently, and many of them, actually most of them, are sponsored by the states, country level states. It's not just individual hackers. These are so actually this is a side note, but I learned when I was at Google, I learned about the attack patterns, and they usually they can find out. For example, usually the attack activities start around the morning time in somewhere in some geographical region, and the attack usually stops around the noon because they have to get lunch, right? And yeah, and usually the attack goes down during the holidays, right? So that way they can guess, oh, this attack is coming from certain time zone and certain cultural background, right? So anyway, so these are mainly state-sponsored cyber attacks. And how do these attacks work exactly? So let me actually, how many of you heard about Stuxnet attack? Stuxnet. Okay, good. How many of you heard about this Triton malware attack? Basically, okay, good, very good. Yeah. This attack is a more advanced version or evolved version of the Stuxnet, and the state-sponsored malware targeted a petrochemical plant in Saudi Arabia, and the attack worked and tried to release toxic gas and cause explosion, right? But fortunately, the human operators were able to shut this down before this physical harm or physical damage was started. So this attack worked. It almost caused physical harm, but fortunately, it didn't cause physical harm. And if you look at how this attack started, you will see that although there was no clear evidence found, researchers highly suspect that it probably started with a phishing attack of the insider account, right? And that's how the malware was introduced, the IT network, right? The general purpose computing network, and it infected the systems performing industrial control systems, and finally it targeted certain type of this hardware and launched this attack, although the attack itself was not successful. And this is another attack that happened about 4 years ago, and actually this caused a disruption in eastern states of the United States. And it was a ransomware attack, right? So if you think about ransomware attack, you may think, oh, it's just a data breach, right? But if you can launch ransomware attack on a critical operational data of critical infrastructure, it can actually cause physical disruption. So actually, it caused fuel shortages in eastern U.S. for 6 days. And again, we suspect that it started from the leaked passwords that were stored on the dark web, right? So these attacks initiated from phishing or account takeover attacks or password leak attacks. And it's not all actually. There are even more vulnerabilities for critical infrastructure, and these critical infrastructure are actually physically exposed, right? So, for example, if the attackers want to physically access some critical components of the critical infrastructure, they can. So it's not just about cyber attacks, but we need to be prepared for physical attacks and fallback mechanisms to deal with such vulnerabilities and threats. So, and even recently, the threats are getting even smarter and more intelligent thanks to the generative AI. And thus, my claim here, as long as your system is connected either via computer networks or either via human users or physically, the complete prevention of cyber attacks will be nearly impossible. So we need to be prepared to mitigate when the attack happens. And I'll show you some of my thoughts in the next section of my talk. So possible future attack patterns will show these roughly these 3 steps, starting from the compromise. So the malware or the attacker need to compromise some insider accounts or computers via zero-day exploits or system vulnerabilities, which will be harder unless you're state-sponsored hackers. And there are actually relatively easier ways to compromise insider accounts or computers, and they're phishing, social engineering, and leaked passwords, right? Because humans are the weaker links to the critical infrastructure system, and some attacks will leverage physical proximity, like side channel attacks. I'll talk about that later. Yeah. Thus, some intrusion will always be possible in the future. And as a second step, once the malware or the attackers compromise one of the insider accounts or insider computers, they will start searching for more juicier targets. And this step is sometimes called reconnaissance stage. And these malware or attackers will monitor silently and hide and wait for a chance. So how many of you heard about IDS, intrusion detection systems? It's a jargon in cybersecurity. Oh, okay, great. That's great. So although we have lots of IDS, they may not be able to detect certain malware because they are usually based on certain anomalies. So for example, if the malware is silent, right, there won't be any anomalies or signature-based. So if it's a new malware, right, just created and never used, then signature-based IDS won't work. So yeah, intrusion detection beforehand may not always be possible. The third step, until if the malware or attackers will wait until the right time and launch attacks. For example, sending destructive control signals, like in Stuxnet, they accelerated the centrifuge of the nuclear reactor, caused the explosion. And at this point, at this third stage, it's a matter of mitigating and limiting damage. So sometimes it's not enough to just support for a simple shutdown and restart. And timing of the detection will be critical, and it will require immediate decision making and quarantine. And we will need some fallback mechanisms, for example, keeping the system operational without the internet or communication. And resilience and redundancy will be the key to keep the availability of the system. And there always should be a way for allowing timely human intervention, as you saw in the Triton malware attack. So yeah, research questions, because we're academics on this interconnected critical infrastructure. So first, we cannot give up the benefits of the internet connectivity. Now, it's not really possible. So how can we ensure the critical infrastructure is still safe, even when it's under cyber attacks over the internet or physical attacks? And that's one research question. And the second research question is, how can we prepare for the future attacks? Because future attacks will evolve and become more intelligent, and it will be more challenging to defend against. And third, how can we deal with these various challenges in making interconnected critical infrastructure secure and safe? So I'll go over some of these challenges. So first one is heterogeneity. So these systems by nature are very diverse. It's not just a single computer or homogeneous server computers. It may include sensor networks or actuators, and different layers of networks and different levels of computation resources, and even different types of requirements and resource availability. And these systems may differ from each other in terms of connectivity. Maybe some of the computing systems use wired communication, while other systems using wireless communication. And yeah, each system will be different. For example, nuclear facility will be very different from building management or transportation systems. The second challenge is operating in open or even hostile environments. So attackers may have physical proximity or wireless network access on this IoT device. So let me go over some examples. And this is research from KTH in 2020. And the researchers were able to attack the Bluetooth communication, the encrypted Bluetooth communication, by using something called side channel attacks. So side channel refers to any non-regular channels other than regular means of communication, like network protocols. That includes power, thermal, radio signal, or even sound, used to extract certain information. And in this case, they leveraged the far-field electromagnetic emissions from Bluetooth communication, and they were able to recover the secret key used for AES 128 cryptographic standards. So AES is the encryption mechanism basically used everywhere, and they were able to hack into this secret key of AES by using deep learning methods. So actually, if you read this paper, you will see that the attack itself is not very complicated. It's pretty simple, but the novelty is they used this side channel, and this sounds scary because if someone listens to your Bluetooth communication within, so it's 15 meters or 50 feet, it's not very far. It's from here, probably here, from there, right? So, yeah. And this is second example is from University of Michigan, Ann Arbor, and probably almost all of you saw this traffic controller, right, on the streets. So anyone can have access, physical access, or try to mess with this. And they launched a simple replay attack. So replay attack is just Kafka listening to the communication and replaying some of the messages to compromise the traffic controller. And yeah, scary enough, they were able to make all these traffic lights green, right, to cause the accidents. So the takeaways from these two examples is that because of the physical proximity and wireless access to this critical infrastructure, there is a higher risk of being compromised. And also, we must be able to revoke access of compromised these IoT devices. So we need to have an assumption that any device can be compromised at some point. And another challenge is scalability, the sheer number of devices and the sheer volume of the data used for this critical infrastructure have been increasing and will increase. So zettabytes, so if you know terabytes, right, tera, peta, and exa, and then zettabytes. So 1 zettabyte is billion terabytes, and the total traffic nowadays is almost 80 zettabytes, and it's been increasing. Okay, so although I've been focusing more on the cybersecurity aspects of the critical infrastructure, let me look into another important aspect, timeliness or real-time requirements, real-time responses. And it's important to guarantee low latency and real-time responses for critical infrastructure. So if you imagine, for example, connected autonomous vehicle performing emergency steering maneuver, then it's important to trigger this maneuver in time to avoid sudden obstacles, right? So yeah, failure to respond timely can lead to catastrophic results. So thus, security protocols operations must be agile and prompt. So just summarizing the challenges I pointed out, of course, it includes the safety, security, real-time response requirements, and the challenges include heterogeneity, hostile or open environment scalability, resource constraints, usability, and also sporadic or intermittent connectivity and high dynamicity. And actually, this has been emphasized for years now. It started, 2021 by an executive order on improving the nation's cybersecurity, especially for the critical infrastructure. So yeah, let me discuss more research questions around the interconnected critical infrastructure. So I talked about connectivity, security and safety, and timeliness. Actually, there is a tension between connectivity and security and safety. So for example, if you have better connectivity, actually you opens more doors for the attackers as well. And there's a tension between security, safety, and timeliness. Also, there is a trade-offs or design considerations around whether we want to prevent such threats from happening at all, or detecting if it happens, should we focus more on detection and response of such attacks, assuming that they will always happen. So let me go over some of my research ideas around these three tensions. The first one is connectivity versus security safety tension, right? And one possible solution that I've been working on is while making the system is securely connected to the internet, providing a capability to be safely disconnected from the internet when it's necessary. So for example, if your system is under attack of denial of like distributed denial of service attacks, you wanna shut down the ingress traffic to your system, right? Incoming traffic. Or if you know that certain system is compromised, then we want to quarantine such system from causing more harm to connected systems. So this is, I'll go deeper into this solution later. And another tension is timeliness versus security and safety. So security processes take some time. For example, we may need extra communication steps for authentication and authorization or access control. So ongoing work, one of my ongoing projects is to hide this authentication latency by predictive propagation of authentication information in connected autonomous vehicle environments. So for example, if you know that this Eagle vehicle is traveling at 40 miles per hour to this direction, and if you can predict that this car will encounter this connected infrastructure sensors or the edge computing systems or other cars, then we can propagate authentication information of this car to these other vehicles or the traffic infrastructure that this Eagle vehicle will encounter soon. And yeah, that was more about this security side. What about timeliness versus safety? So redundancy is a mechanism to enhance reliability and availability, thus safety of the system. So for example, redundant computation using redundant executions or processors, or redundant copies of data, or redundant storage, or using checkpointing validation. These all are useful for improving the safety or reliability and availability of the critical infrastructure. However, redundancy can also take some time and delay responses. So one of the ongoing research with my students is to come up with a deterministic model of the fault-tolerant real-time software, where the software runs redundant executions to ensure the reliability, but at the same time, without missing the deadlines imposed by the real-time constraints of the system. And the third tension was the detection versus mitigation for the robust access control. And this is one of work from my PhD dissertation called Secure Migration. So I'll talk about this a little bit more later, but access control is important to ensure the securely connected systems. And by using replication and distribution of this access control information among multiple nodes, we can ensure that even when one of these nodes are become unavailable, we can recover this access control services. Okay, so yeah, I went over future attacks, research questions, and challenges. Let me move on to more technical topics of my research work. So yeah, as you have seen so far, protecting critical infrastructure from failures or attacks is very different from protecting general purpose computing systems. So we need to consider the system level design solutions instead of just focusing on the cryptography and information theory. Although these are very important, but yeah, I deal with system level design solutions for cybersecurity for critical infrastructure. So my work is many of my approaches are around this concept of authorization and authentication. So I'll briefly explain this. So authorization, or often also called access control, is about the process of allowing or denying access to certain resources. For example, can I enter this building, Donald Brand Hall, after hours? Or can I access Chrome user activities? Or can certain machine be on the UC Irvine network? These are all related to access control or authorization questions. And it includes the process of revoking access. So if you imagine if you lose your ID card, then its access should be revoked. Right? And authentication is, I consider this as a prerequisite for access control because it's almost nearly impossible whether to make the decision whether we want to allow or deny access without knowing you or your device. And this is the questions are like whether this person is a member of staff at School of ICS, UC Irvine, or a security admin of Google, or this machine, whether this machine is registered with the UC Irvine network. So, yeah, this is one of my major research projects called Secure Swarm Toolkit, and this is an open source software toolkit for locally centralized and globally distributed authentication and authorization services for internet connected cyber physical systems or critical infrastructure. And this received the ACMI EEE Best Paper Award in CPS Week 2017, and it has disseminated 14 publications so far, including journals, IoTDI, SafeThings, Smart SP, or SIGMOD. And I'll go over some of these awards later. And yes, let me explain what this locally centralized and globally distributed means. So yeah, this is based on the concept of edge computing, where we leverage the devices at the edge of the computer network. And this software, special software called Auth, provides authentication and authorization services for locally registered computing nodes. Okay, so it can provide tailored and low latency access control services, and also it can perform immediate quarantine and access revocation. And it's very lightweight, so it can work with any almost any types of devices, and it's designed to work even when there's no internet connectivity. And in the meantime, these auth entities are globally distributed and they're decentralized, so they are more scalable and more reliable and robust thanks to the redundant architecture. And scalable with increasing number of devices and traffic. And it can support heterogeneous security mechanisms. So for example, we can choose to use cryptographic standard with low energy consumption, or we can choose to use the mechanisms with more security guarantees, depending on the security requirements of the systems, and it's been formally proven to be secure. So I just realized that it's already 11:46, so I'll speed up a little bit. So yeah, I briefly mentioned about this, but because of the decentralized structure, we should be able to safely disconnect from the internet or safely quarantine the compromised systems. And it provides a programming model API designed for non-security experts, so that this SST secure control kit can be applied to different types of heterogeneous systems. And thanks to that, we extended the SST for secure, reliable, low-cost storage of distributed data used for IoT. So yeah, if you imagine the data, the volume of the data collected by autonomous vehicles is huge. It's in terms of terabytes or tens of terabytes nowadays per day. So it's important to provide secure yet cheap storage for such systems. So yeah, my team developed a lightweight access control for highly decentralized and distributed file systems such as IPFS. It's very similar to BitTorrent, peer-to-peer open system for managing data without a centralized server. And yeah, so I talked about data security, but yeah, data security and critical infrastructure security may seem orthogonal, but actually they're closely related. If you recall the ransomware attack on Colonial Pipeline, which caused fuel shortages for several days in eastern US. So possible solution is, of course, redundant and distributed critical data. For example, if you have multiple copies of the critical data, even one of them is under ransomware attack, you may be able to recover the critical data from the redundant copies. However, that also increases security risks because there are more points for the attackers, and it's not trivial to securely manage and coordinate the large scale frequently updated data. So this is research work in collaboration with my research team and my coworker, Dr. Zhao Chao at Arizona State University, and we used SSD to allow secure, fine-grained, and robust access management to disaggregated storage, storing the data over multiple data centers. And the auth of the SSD toolkit is to manage this access, secure access through the multiple data centers. Let me actually even more speed up. This is another work for protecting legacy critical infrastructure. And we've been working, actually, this is a rover that we demonstrated 2 weeks ago at CPS Week at Student Center, UCI. Yeah. And we've been working on connected autonomous vehicles, and we've been also working on digital twins for advanced manufacturing in collaboration with HP Labs. So of course, security and safety are important for all these systems, and multidisciplinary research is really the key to their security and safety. So in summary, critical infrastructures are connected to the internet, and they're under constant risks and threats. And threats are evolving, so may not be able to prevent completely. We need resilient, reliable, scalable, and low latency security and safety solutions. And balancing these tensions between safety, security, timeliness, and connectivity is important, and also multidisciplinary research is essential. So thank you very much for your attention, and I'll be happy to take questions.
Thanks for the great presentation. I had one question about, so you mainly talked about the internet. I was wondering, do the mechanism that you developed apply to other IoT protocols, let's say NB-IoT or LoRaWAN? And are they, do they also improve security, or they just focus on network and other things?
Yeah, great question. So this is the protocol used by the Secure Swap Toolkit is on application layer protocol. So it runs on TCP, and it also runs on UDP actually, with some restrictions. And it also runs on other types of networks. So I tested on Bluetooth, but I haven't tested that on LoRaWAN, but we should be able to run it because it's application layer protocol, and it's very simple. And sorry, what was your second question?
So do these new protocols improve the security, or they're not relevant to security at all?
Oh, you mean the protocol of SSD or?
No. Maybe my question is.
Sorry, I didn't.
Yeah, my question is mainly about those protocols. Do they also improve the security themselves, or they are not related to
Okay,
security?
great question. Okay, so there are security solutions for, if you imagine the OSI layer protocols, right? So for example, for wireless protocol, we have WPA, right? And that's mainly for end-to-end encryption between these physical or network nodes, right? But it doesn't have features like access control. For example, it'll encrypt the communication between them, but it doesn't have idea whether we should allow this guy doing certain things, right? So yeah, they are all actually essential parts of the security of IoT or interconnected infrastructure, but they have different roles. Yeah, that's my opinion. Yeah, thank you. Yeah. Any other questions? Oh. No questions? Maybe I can talk a little more about where I am. So I started at ASU 2 years ago as an assistant professor. So I'm still an engineer in my faculty career, and I'm very open to collaboration. So if you think any of these projects sounds interesting to you, please feel free to reach out to me. My first name is not common, so if you search for Hokeun, my first name or Hokeun Kim, actually even if you make typo, you should be able to find my name if you roughly remembers my name. And yeah, you should be able to find my personal page and Lab's website. And we have been really working really hard to improve the documentation of this project. So yeah, I think the only major dependency to run this program is OpenSSL. It's it's open source library for standard cryptographic applications. So yeah, please feel free to use that, and please feel free to provide feedback. Oh, this part of the toolkit is difficult to use, or we get an error when we use the toolkit. Yeah, just let us know. Yeah. Any other questions?
We're not in a hurry, but I just wanted to, since he was talking about potential projects, we are actually working together on a smart agriculture project because it has issues regarding, wide scale deployment and connectivity issues and security. He works on the middleware and security side. I will work on the sensors and accelerator side of things to ML accelerators at the edge and things like that. So if you're interested in this general topic, you can also reach him through me. So, and he's also genuinely, easy to approach person. So I highly recommend if you're interested.
I don't have many students in this summer. Actually, I think it's still spring quarter here. Yes. Right? Yeah. But yeah,
Finals are coming.
the summer, because Arizona State University is semester based. Summer just started, so I have more time. So I'll be happy to chat with you about this. And now Arizona is in the same time zone as California, so it's easier to the meeting. But yeah, actually we will be 1 hour ahead as soon as the daylight saving ends, because Arizona doesn't want to save daylight. We have enough daylight already. So yeah. No questions? Okay, we can wrap up. Yeah. Thank you. Very nice to meet you. We're going to lunch soon.